So in this lesson, we're going to look at one of the behaviors of light when it's modeled as a wave, and that's the behavior of reflection. So let's look at our learning objectives. The first is that we be able to explain the law of reflection. And then second, locate where the images are formed by a plane mirror. Now, when we say plane mirror, that's simply a flat surfaced mirror, like a tabletop or a wall. So the first concept we need to talk about is that reflection occurs along line of sight. Now, what do we mean by that? So let's say you have your eye over here on the right, and you want to observe, right, the light coming from this little lightsaber here. If we shine a light on it, we see that the light reflected off of Yoda here back to our eye is in a straight line, right? It goes from the floodlight to Yoda in a straight line, and then from Yoda reflected back to our eye in a straight line. So in order for us to observe reflected light, we have to look along what we call the line of sight. Now, what is the relationship that determines, right, the actual line of sight, the path that that reflected ray is going to take? So let's define reflection, and then we'll get into the actual law of reflection that defines the path it takes. So reflection is the bouncing back of a particle or wave that strikes the boundary between two media. So a very broad definition here. So typically, reflection occurs when we have a boundary between materials like air and glass, or glass and metal. This example would be of a basic mirror, right? The mirror is made up of a piece of glass, and the backside usually of the mirror has a thin layer of metal, often silver for a good quality mirror, deposited on the back of that glass. And the light rays, as they shine down, they're going to be reflected by that boundary between the glass and the metal or silver. So if all of that energy is reflected, that's what we describe as full reflection. So no light or very, very little light actually passes through the mirror. We can also get reflection between an air and water boundary. But some of that light is going to continue on into the water, pass into the water, and some of it gets reflected off the surface, right? We see the glare that comes off of water, a lake or a river or the ocean. So we would describe this as partial reflection. So whether it's full or partial really depends on the media itself. Glass and metal typically will produce a full reflection. Now, let's get to this concept of what determines the path of the line of sight that a light ray takes as it's reflected. So that's governed by something we call the law of reflection. The angle of reflection for a wave that strikes a surface is equal to the angle of incidence. So angle of reflection equal to the angle of incidence. Now we're going to use the Greek letter theta. It looks like an O with a line through the middle. And the subscript R represents the reflection angle, and subscript I represents the incident angle. Okay, so this says the incident angle is equal to the reflected angle. Now, how do we actually define these angles? So here's our reflective surface. Here comes a light ray, and the ray that is coming into the reflected surface we call the incident ray, and the ray that is reflected or bounced off the surface we call the reflected ray. Now, in order to define the angles here, they're always going to be with respect to what we call the normal line. Now, normal in this case, think of it as just another word for perpendicular. We're always going to draw the normal line perpendicular to the reflected surface. And the angles will always be measured from the normal line or relative to the normal line. So our incident angle would be between the normal line and the incident ray, and the reflected angle would be between the normal line and the reflected ray. And what the law of reflection says, that the the incident angle is equal to the reflected angle. Or another way to think about it is angle in equals angle out, always with respect to the normal line. All right, so let's see if we understand these concepts here. A couple questions. First one, which angle is the angle of incidence? So if you look at the diagram on the right, we have 4 different angles we could measure or define, A, B, C, and D. Which one is the incident angle? Well, the incident angle would be angle B, right? Because it's always with respect to the normal line. The solid line here is perpendicular to our mirror surface. Which is the angle of reflection? That would be C. Again, always measured from the normal line to the, in this case, the reflected ray. All right, let's take this the next step further. If we have a beam of light reflecting off the surface here, can you look at the path that it would take as it's reflected, and which letter would be, or card would be illuminated by that light beam? Would the light reflect to card A, B, C, or D? Well, if you can imagine our normal line, right, that we would draw in there, and the angle in has to equal to the angle out, or incident has to be equal to the reflected angle, we would see that that light ray would reflect onto card B. So that would be the only card that we could observe. If we wanted to see angle A, right, we would have to reduce the angle. If we wanted to see card C or D, we would have to increase the angle in order for it to be reflected on those surfaces. Okay, so let's apply this, and a little more complex set of calculations we'll do around the angle. Okay, so let's pretend this black line that we have, these 3 segments of it, are a mirrored surface. Okay, so the incident ray, you can see in the red line, is going to first strike the glass surface at a 45-degree angle, and we want to know what path will this light ray take as it reflects off of these mirrored surfaces. So if we were to draw this out on paper, the first thing we always do is want to construct our normal line perpendicular at the point where the light ray hits the reflective surface or mirror. And then whatever this angle is here, well, we could actually calculate that angle, right? Because we know the normal line to the mirror surface is 90 degrees. And we already have one angle that make up that 90 degrees is 45. So the other angle, or incident angle, also has to be 45. 45 plus 45 gives us 90. So the reflected angle will also have to be 45. So that actually gives us a reflected path that is parallel to the bottom mirror. So this light ray will not actually reflect off the bottom or central mirror surface, but now it does strike the mirror on the right. And again, if we construct our normal line, and we know that this angle here would be 45 degrees, therefore the reflected angle will also have to be 45 degrees. So if we had a set of mirrors at these angles, they would basically cause the light beam to reverse itself, right, to come in and then reflect out in the opposite direction, or 180 degrees from which it came in. Let's do one more here. What will the final angle be of the reflection of the light ray? So different angles now, right? It's coming in at 30 degrees relative to the first mirror. So let's put our normal in here. So can you tell me what the incident angle would be, right? 30 plus what gives us 90? Well, of course, that would be 60 degrees. So that means our incident angle is 60 degrees. Therefore, our reflected angle will have to be 60 degrees also. So we know that the sum of all the angles in the triangle, right, have to add up to 180 degrees. So if those two are 30, that's 60. We can now determine the incident angle to the second mirror. 30 plus another 60 will give us 90. And now we can draw our reflected ray at 60 degrees, same as the incident ray. And now we can see, now we can see the path that it would take. So in this case, with these angles, it would, light ray would pass and reflect off of both surfaces. And it's not going to come back in a parallel manner, right? It's going to be in a different direction than what the original light ray was. Okay, but just using some basic geometry and properties of angles and triangles, we can calculate what these various angles would be. All right, so we know about the law of reflection. The question now is, where does the image form of a mirror? Now, what do we mean by an image? If we were in class, we could do this with mirrors and actual objects, but let's say we're going to take a mirror and place it vertically, right, on a line, and we'll put an object in front of that mirror. Okay, in this case, it's just a pencil stuck in a rubber stopper or cork. And if we lowered our eyesight down, we could see that image in the mirror, right? See the reflection of that pencil in the mirror. And then we could try and position another pencil behind the mirror such that it lines up with the image that we see in the mirror. Okay, now we have the actual object, right, is the pencil on the left. What we see in the mirror is the image that forms. Now it's a virtual image, right? We can't actually touch it in the mirror, but we can place another pencil in a location that appears to be where the virtual image is forming. Okay, so the object is the real thing. The image or virtual image is not the real thing, but it's the image that we see reflected off of the mirror. So if we actually move that mirror out of the way, we have two objects, the original object and an object now representing where the image formed. And notice that the object and the image form on opposite sides of the line that represents where the mirror surface was. And they turns out to be the opposite but equal distance on each side of that line. Okay, that's the key concept here in terms of image formation. The image forms an equal distance but opposite side of the mirror. So let's kind of summarize this and draw a little more general form here. Let's say the bird is our real thing, the object, okay? And let's say if we're focused on the light, or the eye rather, of the mirror of the bird, we would have light rays, right, that would come out from the reflected light off of the bird's head or eye and strike the mirror. Now, if we use the law of reflection, right, we can draw in how each of those rays, the three rays, would be reflected back. Remember, angle in equals angle out, measured around the normal line. And it's those reflected light rays that we detect, right, with our eye when we're looking at the bird in the mirror. Now the question is, where would the actual image form? So if we take those light rays and extend them back behind the mirror, we would find a point where they converge. Those extended light rays converge to a single point, and that is where the virtual image would form. So just like the pencil that was equal but on opposite sides of the mirror, we see the same thing here with the image. So let's define this officially. The image position, which we'll call d sub I, d stands for the distance from the mirror, is equal to the negative of the object position. Okay. So if the object position is DO, you can see at the top here, right, I've put in an arrow that goes from the bird to the mirror. Then the image position is going to be equal to the opposite of that. Okay, so the negative sign indicates that it's going to be a negative image. So if the bird were 1 meter in front of the mirror, we would say that the image of the bird is going to form a negative 1 meter, or 1 meter behind the mirror. Now, the other thing we can talk about is the height or size of the object. So if the bird is of height h0, then the image of the bird is also going to be at the same height. And these rules apply to a plane mirror, in other words, a flat mirror. Now, you've probably all been at a carnival, or often stores will have curved mirrors right in the corners of them. And there, these rules about the image height being the same as the object height don't hold up, right? So these rules about position and size of the image apply to a plane mirror. If the mirror is curved, we're going to have very different results. All right, so last example here. Let's see if we can kind of put all this together and apply these concepts. So we have 7 people here on one side of a mirror. The line in the middle represents the mirror. And we want to know who person A will be able to observe in the mirror. Okay, now how would we do that? Well, let's take each person and draw a normal line, right? So if we were to be able to observe person D, right, their image would form equal and opposite on the other side of the mirror. And then we could say the same for all of the other images for A through G, right? They're going to form on the opposite side and equal distance. Okay, so now let's go back to that question. Which images can person A observe? So can person A observe image G? And the answer would be yes, right? Because if the reflected light of G onto the mirror surface comes back to A, that would abide by the law of reflection. The incident angle is equal to the reflected angle. And then if we take that reflected line and extend it back on the opposite side of the mirror, we see that it would lead us right to image G. So object A will be able to see object G. What about the other objects? Well, let's try it for F. Yep, looks like it would work for F. Looks like it would work for E. Now, how about D? So notice, in order to look at image D by line of sight, that line is not going to take us to the mirrored surface. Okay, so object A would not be able to see object D formed in the mirror. Same thing with C, B, and A. Okay, so person A here would be able to see G, F, and E, but not B, C, D, or themselves, object A. All right, let's try another one, this time for E. See if you can figure out which other people or objects E would be able to observe in the mirror. So can they see G? No. Line of sight does not pass through the mirror between E and the image of G. Same thing for F, would not be able to observe F. Now they'd be able to see themselves, right? They're going to be straight across. The image will form directly behind the mirror. They would be able to see object D. They would be able to see object C, B, and they'll just be able to see object A. It'll be right at the kind of far edge of the mirror. So in this case, E is able to see A, B, C, D, and itself. All right, so that's it for this unit. We understand what the law of reflection tells us. The angle in, or the incident angle, is equal to the reflected angle, always measured about a normal line. And we know how does the image form when we look at it in a plane mirror. It's going to form on the opposite side of the mirror, an equal distance that the object is in front of the mirror. And the image and object height or size will be equal to each other. Okay, that's it for reflection. Take a look at the assignment.